flipped classroom video for Mathematics AS Unit 1, Proof and Deduction. So in this video we're going to be looking at what proof is, what mathematical proof is, and we're going to look at deduction and how we construct proofs using deduction. So we're going to start off by considering the question, what is truth? And firstly, in mathematics, mathematical truth comes through mathematical proof. And every proof can, in principle, be constructed using only certain basic or original assumptions, which are known as axioms, and then using logical reasoning, including rules of inference, to develop mathematical truths, mathematical theorems. And it's fair to say that mathematical truth is different in this respect from other truths. This is a picture of a fragment from Euclid's Elements. Euclid was a Greek mathematician writing around 300 BC, and as you can see there's a geometrical diagram there, and Euclid worked with axioms and rules of construction or logical reasoning to create lots of mathematics, and it's still taught today. We also use the word proof in other situations, so I've called that non-mathematical proof, and you'll be aware of statistical proof or statistical evidence, and this gives a certain degree of certainty but not absolute certainty, as in mathematics. And science, for example, relies on statistical analysis and is therefore true in a different way from mathematics. This is another example, historical example from about a bit over 100 years ago, and it's from Principia Mathematica, which was written by Bertrand Russell and Alfred North Whitehead, and this is page 379 from that book, and it took them that long, working from basic axioms and logical reasoning, to arrive at the proposition that 1 plus 1 is equal to 2. Now, whilst that seems slightly ridiculous, because it's obvious that 1 plus 1 is 2, what it shows is that mathematics is mathematicians have tried to give mathematics an absolutely sound basis, so that mathematical theorems are true in a fairly absolute sense. There are other sorts of argument. We have the idea of an inductive argument, and that means deriving general principles from specific observations. And we have empirical evidence, which is information received by means of the senses, and that includes experimental evidence in science and in, for example, legal proceedings. But it's important to understand that those sorts of arguments and evidence supply some but not compelling evidence of truth. So, what are axioms? What are rules? What is deduction? Axioms are statements which are taken to be true. So an example of that is a Euclidean axiom, and this one states that things which are equal to the same thing are also equal to one another, which seems obvious, which axioms are meant to be. They're meant to be self-evident. We could write it out a bit more easily to understand. So if x is equal to a and y is equal to a, then x must be equal to y. A rule of inference is used to deduce new statements from ones which we accept as true. And you already use rules of inference, and you've used them throughout your mathematical learning. And there are all sorts of different rules of inference, but this is an example of one. So we start with two premises. One is that oceans rising imply, and we'll come back to that symbol, loss of coastal settlements, and the second premise, oceans are rising. Now we can then conclude, assuming our premises are correct, that coastal settlements will be lost. Okay, but it's very important to understand that the argument there is sound, but the premises need to be established. And then we have deductive reasoning or deduction, and this ties back to the previous points about mathematical proof. And what we do is we start from something that's true, we use accepted rules of inference or logical construction, and we arrive at a new truth. And an example of that is, if A is bigger than B and B is bigger than C, then we can deduce that A must be bigger than C. And we can write that in different ways, and if you go deeply into this sort of stuff, then you'll find that these sort of statements can be written exclusively with symbols. So that upside down sort of N shape means and that sort of double arrow means implies. So we'll now have a look at proofs by deduction, and we'll have a particular example to work through. So we want to prove that the difference between the squares of any two consecutive integers is equal to the sum of those integers. So the first thing we do is to move into symbols. So we're going to let n, which is a member of the integers, be the smaller integer. So we often use n or m for integers, and incidentally it's worth noting at this point that we sometimes use n squared, obviously, for a squared number. If the question stipulates, or the situation stipulates, an even number, we would use 2n, and for an odd number we can use 2n plus 1, or 2n minus 1 sometimes is more convenient. The other symbols there, that Greek e means is a member of, and the z with the extra line is the set of integers. We also, incidentally, for various other sets, have these double line capital letters. So n is the natural numbers, so that's positive whole numbers. Generally we consider that to include 0, but occasionally not. Q is the rational numbers, that's Q for quotient. R is the real numbers, and C is the complex numbers. And you'll come across them in further maths if you study that, or if you study any higher maths later. So going back to the proof, then if n is the smaller integer of the two consecutive integers or next to each other integers, then the larger one must be n plus 1. So the difference between the two squares will be n plus 1 squared, which is the larger one, take away n squared, which is the smaller one. And if we expand n plus 1 squared, we get n squared plus 2n plus 1, and then we've got our minus n squared at the end. So that leaves us with 2n plus 1. Now it's not totally obvious that that is the sum of the two integers, so we better make that clear. So we have n plus brackets n plus 1, and that's written like that to make clear that we've got the two original integers. And then we can say QED, quod erat demonstrandum, or we can use a square, sometimes people use, or a filled-in square even, and all three of them mean that we have proven what we set out to prove. So we'll start another little proof. Let's have a look. Prove that two odd numbers multiplied together are also odd. Now this is one, you know that. You've multiplied lots of odd numbers together, you've always had an odd number as the answer, but that doesn't prove it. You could do a billion examples and it wouldn't prove it. So we could start this proof with letting our two odd numbers be 2n plus 1 and 2m plus 1. Now we probably for completeness should write n and m are members of the integers, but I won't bother with that just for now. You might want to add it because this is one for you to have a go at. We'll have a look at another deductive proof, this time a geometrical one. You may have seen this before. So we want to prove that the angle subtended at the circumference by a semicircle is a right angle. So we have a diagram, and so the circle round from A to B going upwards is our semicircle. We have the diameter in there, C is the centre, and D is the point to which we've subtended. So how do we prove this? Well, the first thing to do is to put an extra radius onto the diagram. We can then see that AC and CD are equal to each other because they're both radii. This means that ACD is isosceles, and therefore the angle at A and the angle at D are both the same, and we give that a name alpha. Notice that each step is being clearly laid out so that it's easy to follow the argument, the logical argument. We've got another bit of notation here. I'm sure you know this one, but just in case, those three dots means therefore, and you may be interested to know that if you do the dots upside down it means because, so it's like an opposite way round therefore. And this one I'm sure you know, but I've put it in for completeness. If we have an angle DAC with the cap on the A, then that means the angle at A, formed by the two lines that are joining it. So we can do a similar job with the other isosceles triangle we formed when we drew the line from C to D, and therefore conclude that the angle at D in that triangle and the angle at B are the same and they're both beta. That's what I decided to call them. And now we can move into showing what needs to be shown. That statement there says the angles in the triangle add up or sum to 180. So that's the statement we're using to prove this. And from that we can say that alpha, which is the angle at A, plus alpha plus beta, which is the angle at D, plus beta, which is the angle at B, in the red triangle must add up to 180. Therefore we have two alphas, two betas adding up to 180, divide by 2, and we have alpha plus beta equals 90 degrees. And therefore the angle at D from A and B, so the angle subtended, is indeed 90 degrees. And we've finished the proof, so we put that little square there. So now we have another proof. Prove that the angle subtended by an arc at the centre of a circle is twice the angle subtended at any point on the circumference. So we'll have a diagram for that. So we can see we have the arc is from A to B. So when we subtend angles from there into the circle, we go to C and to D, and what we're saying is that the angle ADB is half of the angle ACB, or actually the proof is saying the angle ACB is twice the angle ADB. So we would put our line on, and then this is for you to have a go.